back to my channel. In today's video, I would love to take you on a journey across the world of mathematics. As you can see behind me, I've drawn this colorful map of mathematics especially for today's video. A few years ago, a dear friend of mine asked me to draw a map of mathematics. He was inspired by a video he found on a channel called Domain of Science. It's a nice channel, by the way, you could check it out. I redrew my own version, adding the areas that I love and the ones that I've studied or taught throughout the years. Today I will recreate this map with you, walking through its main ideas, also guided by the Princeton Companion to Mathematics and my own experience as a teacher and student in this beautiful science. And by the end of the video, I will leave you with a little rhetorical question: what can't a mathematician do? Mathematics is often divided into two parts: pure mathematics and applied mathematics. Pure mathematics is about exploring ideas for their own beauty, searching for patterns, structure, truths, simply because they are fascinating. Applied mathematics, on the other hand, brings these ideas into the real world. It's where math meets physics, engineering, biology, economics, and art as well. What's truly wonderful is that these two worlds are deeply connected. Many of the theories that pure mathematicians once developed just for the joy of discovery later became the language through which we understand our universe. It all begins with numbers, the most familiar part of math. From natural numbers to integers to rational and irrational ones, and the special constants like pi and e that appear everywhere in science. And all this is contained in the set of real numbers. Arithmetic is where we learn how numbers behave, how they combine, grow, and balance. Yet even here lies deep beauty. Infinite series, symmetry, and patterns that have inspired mathematicians for centuries. Next, we go to structures. From simple equations, we move to algebra, the study of symbols and the rules for manipulating them. Algebra teaches us how to express relationships and generate patterns. Over time, algebra evolved into the study of deeper structures, such as groups, rings, and fields, that captures the essence of symmetry and operations. Linear algebra extends these ideas to spaces made of vectors and matrices. A language so powerful, it shapes everything from geometry to computer graphics and artificial intelligence. Then comes number theory, often called the queen of mathematics. It explores the properties of whole numbers, prime, divisibilities, and patterns hidden in the integers. What once seemed like pure curiosity now form the backbone of cryptography and digital security. Combinatorics, meanwhile, is the art of counting and arranging, solving puzzles about possibilities. It's the problem solver's paradise, where creativity meets logic. Graph theory explores connections, how points and lines interact in networks. It's now essential for understanding everything from social networks to molecules. In group theory, we study symmetry, the transformations that leave an object unchanged. A Rubik's Cube, for instance, is governed entirely by group theory. Next, we move from numbers to shapes, to geometry. From Euclid's triangle to the beauty of Pythagoras' theorem. Geometry describes spaces and forms. Trigonometry adds motion and measurements. The study of angles, waves, and cycles. Fractal geometry reveals shapes within shapes, patterns that repeat infinitely, just like the patterns in nature, or even the crochet designs I love to create. And then topology, the study of shapes that can bend, twist, or stretch, yet keep their fundamental essence. The classic example, a coffee cup and a donut are topologically the same. Each has one hole. Mathematics is also about change. Measure theory gives us tools to assign numbers to size, area, and probability. The foundation of calculus and modern analysis. Differential geometry then brings measurements into curved spaces. It's how Einstein's theory of relativity describes gravity. And calculus, the great invention of Newton and Leibniz, makes us understand motion, growth, and change itself. And when we use calculus to describe how quantities change over time and space, we arrive at partial differential equations, the language of motion, heat, diffusion, and waves, a cornerstone on how mathematics model the real world. Vector calculus extends this to forces and flows. It's what makes physics, engineering, and even weather models possible. When we apply calculus to systems that evolve over time, we get dynamical systems. Models for everything from fluid flow to ecosystems. But not all systems behave predictably. In Kaya's theory, small changes in initial conditions can lead to huge differences in outcomes, a concept beautifully captured by the butterfly effect. Complex analysis extends calculus into the realm of complex numbers, where geometry and algebra unite. It's one of the most elegant areas of mathematics, showing how something as abstract as an imaginary number can describe shapes, motion, and even physical phenomena. Now we cross into applied mathematics, where theory meets reality. Mathematical physics uses equations to describe the laws of nature, from quantum mechanics to cosmology. Mathematics also supports other natural sciences. Mathematical chemistry models molecular interactions, and biomathematics explore growth, epidemics, and ecosystems. Engineers use mathematics extensively to design, control, and predict. When exact solutions are impossible, numerical analysis provides approximate ones, often using the finite element methods. Probability helps us model uncertainty, from rolling dice to predicting weather. Statistics turn data into understanding, helping us see patterns hidden in numbers. Game theory studies strategy and decision making, the mathematics behind competition, cooperation, and choice. Mathematics drives modern finance and economics, modeling risk, growth, and market behavior. Optimization teaches us how to find the best possible solution under given conditions, minimizing cost or maximizing efficiency, an idea used everywhere from business to AI. Computer science and mathematics are deeply intertwined. Algorithms, logic, and complexity theory all come from mathematical thought that predates computers themselves. Modern machine learning and artificial intelligence are built on linear algebra, calculus, optimization, and statistics. And perhaps one of the most striking examples of pure mathematics in action is cryptography, born from number theory. When Bob sends a secret message to Alice and Oscar tries to intercept, it's mathematics that keeps their communication safe. Finally, all of mathematics rests on its foundations: logic, axioms, and structures. Mathematical logic ensures our reasoning is sound. Set theory defines the universe where mathematics lives. Category theory unifies different branches under common patterns. And Gödel's incompleteness theorems remind us, even in this perfectly logical world, there will always be truth that cannot be proven. So here it is, a glimpse into the universe of mathematics, a work created by human imagination, yet capable of explaining everything around us. You see now, mathematicians are really powerful. Not powerful because of titles or degrees, but because we learn to think, to reason clearly, to create, to connect, to solve, and to imagine. And that power is not limiting only to teaching, as many people think. Though teaching is one of the most noble and meaningful things we can do, mathematics give us the ability to contribute to science, to art, to technology, and to understanding life itself. I hope this little journey helped you to see mathematics not just as a subject, but as a living thing that connects everything around us. Be prepared, next week our lesson will begin. Different series will open simultaneously, from foundations to calculus to linear algebra and more. So grab your pens and notebooks and stay tuned. And if you haven't yet, please subscribe to the channel, tap the bell to get notified, and tell me in the comment, what can a mathematician do?